this is a definition of vertical asymptotes you really haven't seen before because you haven't known about limits before. So at a vertical asymptote, if the limit as x approaches c from the right of f of x equals positive or negative infinity, or the limit as x approaches c from the left of f of x equals positive or negative infinity, then x equals c is a vertical asymptote. So if we kind of sketch ourselves a little graph right here of what that looks like. If we've got some value c right here, I'm going to put myself a dotted line right here. If the limit from either side equals positive or negative infinity, it doesn't even have to be both sides, at either side, then you have a vertical asymptote. So as you get closer to that line, if your value goes up and up and up and up and up and up, like that, approaches positive infinity, that would be a vertical asymptote. You don't have to have something on the other side. You could. It also could approach negative infinity. You might have something that, it could do crazy stuff here, but then maybe it does like this. It gets closer and closer and closer to that line, that vertical line. Those are vertical asymptotes. So you guys have been familiar with that idea, I think, as far as the limit notation. That's a little bit new. So any value that causes the denominator of a simplified function to equal 0 will be the location of a vertical asymptote. So we've already done this a little bit. We were looking at discontinuities, right, in one of the earlier sections. We looked at discontinuities. We were finding where we had vertical asymptotes. So if we these are not dealing with limits. These are just asking us for those vertical asymptotes. For number 1, who can tell me where I would have a vertical asymptote for that one? -2. So we'd have vertical asymptote at x equals -2. And whenever you write it, make sure you put x equals -2 because that's the equation of the line. If you just say -2, it could be x, it could be y. So you want to put x equals -2. All right, great. We got vertical asymptotes there. What about number 2? That's one of them. It's also going to be -2. Because like if we factor this, we'll get x minus 2, x plus 2 here. And so we'll have vertical asymptotes at x equals 2 and x equals -2. Doesn't cancel with the denominator, with the numerator, because the numerator won't factor. X squared plus 4 will not factor. Oh, what do you guys think about 3? Trig, everybody's favorite. Now, if it was sine or cosine, what would we say for vertical asymptotes? If it was a sine or cosine? Do sine and cosine have vertical asymptotes? They do not. So we would not have any vertical asymptotes if it were sine or cosine. All of the other trig functions do have vertical asymptotes. Okay. Cotangent, it is helpful for me to think of this. This is cosine of pi over x, or pi x over sine of pi times x. Okay, because cotangent is cosine over sine. So, what would give us a vertical asymptote? Anywhere the denominator equals 0, right? So we're worried about this being 0. So, one of the numbers that it's going to be is 0. Here's the problem with trig. It makes this problem more difficult. If you were just asking for like principal values, or if they like limited this off to a certain increment, 0 is probably going to be your answer here, because at 0, sine of pi x would be 0. Is sine only 0 once, or does it happen over and over and over and over again? Over and over, right? So if we think about it, definitely 0 is going to be one of our answers. But if we think about that unit circle, sine is going to equal 0 right here at 0, because that's 1, 0. It's also going to equal 0 over here at pi. That's -1, 0. Where else? Okay, it is those two places. So like if we're looking at the unit circle, it's only those 2 points. Do those points always have the same name. I can call them 0, I can call them pi. Where's 3 pi at?
It's still at pi, but it's like the next circle.
Right, it's like the next increment over, right? So like, here's 0, here's pi. 0, what else can we call 0? 2 pi. What else could we call pi? 3 pi. 4 pi. 5 pi. 6 pi. 7 pi. 8 pi. Oh, we could go the other direction, right? We could do, this is going to be negative pi, negative 2 pi, negative 3 pi, negative 4 pi, right? Sine of pi x is going to equal 0 at a lot of different places here. So the one way we can write this is we could say that this is going to equal 0 at k, make sure I'm doing this right, times pi, where we're going to write down here k is an integer. Right. That would also include 0, because k could be an integer, which could be 0. 0 times pi would be 0, right? And then it would be 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, or it could be negative 1, negative 2, negative 3 pi, all of those, right? Now, a little trick here. Sine of pi x. This has a pi x instead of just a x right here. So the whole thing is going to equal 0 at k times pi, but the pi is already there inside of this, right? So, like if we want to plug in 3, we're really plugging in 3 pi. So pi x equals k times pi. We would divide that pi off from both sides. X would equal just k. So basically any integer value, 0, 1, 2, 3, 4, 5, or negative 1, negative 2, negative 3, negative 4. Those are a little trickier. A lot trickier. Now, these can be made a little bit easier if they only ask you to look from like 0 to 2 pi. Then you wouldn't have multiple answers, and sometimes they will do that on these problems. They'll say from 0 to 2 pi, where do you have a vertical asymptote? That makes it a little bit easier to give your answer. All right. Okay, this one is also a vertical asymptote problem. I didn't copy over the directions, but vertical asymptotes here as well. Lily, what would we need to do? Wonderful. So if we factor here, we got x minus 2, x plus 2 on the bottom, x plus 4, x minus 2 on the top. Okay, so we would have discontinuities. We'll have discontinuities at x equals 2 and x equals negative 2. So I'll have some type of discontinuity. But at x equals 2, Luke, what kind of discontinuity do I have? I've got a hole, right? Because the x minus 2's will cancel. So this is a hole, or a removable discontinuity. That is not a vertical asymptote. But x minus 2 is a vertical asymptote. There. Okay, questions? Right, we've already done this a little bit, so hopefully this is, maybe the trig might be a little confusing, but we've done this some. So, infinite limits are going to occur at vertical asymptotes. Whenever we do a limit like this, it may not immediately be clear that we are looking at something that is going to have an infinite limit. But if I look at this problem, if I try to plug in, what's the first thing we are always supposed to do? Direct substitution, right? I've got to plug that number in. So if I try to plug in 1, I would get 1 squared minus 3 times 1 over 1 minus 1. Oh, this gives me 1 minus 2. I'm already jumping to the answer. 1 minus 3 over 0, which gives me negative 2 over 0. That is not 0 over 0. 0 over 0 would tell me to factor and try to cancel and that sort of stuff. Try to do something else. But that tells me that the limit does not exist. However, let's pretend that this is a multiple choice question, and we look at our answer choices, and there is no option for the limit does not exist. But we do see there a positive infinity and a negative infinity, right? So if does not exist was an option, you could put that down. That would be correct. Infinite limits do not exist, right? Your speed limit cannot be infinity. It's not really a limit if it is infinity. But in this case, we need to decide if it's positive infinity or negative infinity. Now, there's not a great mathematical way to do this. I'll be honest, I don't really like doing these problems very much, especially if they show up on the calculator inactive section, and sometimes they do. So if this were calculator active, type that into y equals, look at the graph. If you can't tell from the graph, put some numbers in the table, see what's happening. So sometimes these will be on calculator active. Occasionally they put this on calculator inactive. If they put this on calculator inactive, you're going to have to do a table by hand to see what's happening here. Thankfully, it's at least just from one side. So if we think about making a table for this, we've got our x here and our y here. We're approaching 1 from the left, so we need numbers that are lower than 1. I'm going to try -1. Sometimes it'll help to go a couple numbers below. Sometimes you can see the pattern. So if I have -1 squared minus 3 times -1 over -1 minus 1, that is going to give me 1 plus 3 over -2, which will give me -2. If I plug in 0, I'm going to get 0 minus 0 over 0 minus 1, so I'll get 0 there. Right now, it looks like we're increasing, right? But -1 and 0 are numbers that have a lot of properties where, like, something that is happening over time is not going to be the same for -1 and 0. So I would not feel safe making the assumption that this is going to be increasing, going to positive infinity here. The answer should be positive infinity or negative infinity. We should see that, but we need to go closer to 1. So 1/2. Do I want to use I think I'm going to use fractions. I like fractions better. I don't know if I can convince you guys. Usually I can. Usually by the end of this class, I can convince a lot of students you're just better off doing fractions than trying to do decimals with this, because if you try to do decimals, you're going to end up in long division with decimals, which is a pain. But you could do it that way. So we'll have 1/4 minus 3/2 over -1/2. And then you got to get common denominators here to subtract. So this would be 6/4 if we did common denominators. 1/4 minus 6/4 is going to be -5/4 over -1/2. How do we divide fractions? Flip and multiply. We get positive 10 over 4, so 2.5, 2.5. For that, so we plug in 1/2, we get 2.5. Now, if this is on an exam, I was crunched for time, I'd probably say infinity and go on with it. Let's do one more just to feel a little better. Let's do 1/10. 1/10 is pretty easy to work with because 10 is easy to deal with. So if I do 1/10 squared minus 3 times 1/10 over 1/10 minus 1, we get 1 over 100 minus 3 over 10 over -9 over 10. Got to get common denominators in that numerator. I can do that just by putting that 0 right there. So I get -29 over 100 divided by -9 over 10. So -29 over 100, or 100 times 10 over -9. So it's going to be 290 I've done something wrong. It's negative 9/10, right? It'll be 10 over 10. So I feel like we should get a bigger number, but we're going to get a number that's smaller than 2.5. Oh, gosh, yeah. That's my problem. This can still help. Okay, I told you guys I mess this up all the time. Is 1/10 closer to 1 than 1/2? No. We should have done like 9/10, but then that would have made it still with a 9. But this can still support our answer here. So that we don't have to go back and do another one. I hate these problems. But they put them on there sometimes. So I got like 29 over 90. But this right here really should not be where it's at, right? It really should be right here in my list. So would we still be seeing our values increase? We would. I should have done like 3/4 or 9/10 or something like that. Instead, I made the same mistake I was talking about the other day, where I think that a half pounder is not as good as a double quarter pounder. Why did I do that? Well, anyway, I did that to make sure you guys were paying attention. Thank you. So we're not going to do another one of these because we have exhausted our fraction capabilities and tolerance for the day. We see that we are increasing right here, and that means that we are going to say that this limit is positive infinity. Okay? I don't love these problems because it's basically the only way. If they have not given you calculator active section. If it is calculator active, graph it, put it in the table. Either one of those is going to be way faster than what I just did. Right? So, let's continue on. Okay? Some properties of infinite limits. If I know that the limit of f as x approaches c is infinity, and the limit of some other function has a value L. So L could be anything. It could be 7, it could be 10, it could be negative 300, whatever. Actually, I think L does have to be positive here. No, they even put a condition here. So if I add the limits of f of x plus g of x here, the properties of limits tell us we can do those things separately. This is going to end up being infinity plus L, but infinity plus L is just going to be infinity, right? If I'm multiplying, if L is greater than 0, I will get positive infinity. If L is less than 0, I will get negative infinity. Okay? Look at this one. This one's a little bit different than the others because they basically just apply properties we've already known. The quotient property, it's incorrect to mathematically say that whenever you do this that you get L over infinity. Like if I put an equal sign there, nothing can really equal L over infinity, but we can think of it. So the top of this limit you would get L, and the bottom you would get infinity. Why is that 0? That bottom's getting bigger and bigger and bigger, right? L is staying the same, right? So just like we were talking about yesterday with our limits as x approaches infinity, this is similar to what's happening here. So if you got something where the limit is going to be infinity on the bottom, that's going to give you 0 for that. And these limits also apply where we have negative infinity. We'll just get negative infinities. The signs will be switched for that as well. All right, so if I have a problem like this, okay, the limit as x approaches 0 of 1 plus 1 over x squared. So I can think of doing, properties of limits tell me I can think of doing this separately. I can do the limit as x approaches 0 of 1 plus the limit as x approaches 0 of 1 over x squared. Now, limit as x approaches 0 of 1 is 1. If this is calculator inactive, which I'm going to pretend like these are because that's the hard part of doing these problems. On the homework, I'm going to not let you use the calculator on part of it, and then I'll let you use the calculator on the other. So if I've got 1 over x squared, if I'm thinking of a table for that, right, if I start at, it's both sides also, if I start at like -2, right, that'll give me 1/4. If I do -1, I plug in -1, I'll get 1. What about if I do like -1/2? 1 over -1/2 squared. How do I square a fraction? You can either think of like multiplying it twice, or you square the top, square the bottom. So you'll just have 1/4 for that. And then so dividing fractions is easy as pie. We're going to flip the second, multiply. We get 4 for that. So what does it appear like we are approaching from the left side? Infinity. What about if I do from the right side? If I change this to a +2, does it change what we get out? Like if I plug in a +2, I'll have 1 over +2 squared. Still gives me 1/4, right? Because we're squaring this, it doesn't make a difference if we do positive or negative. If I put a +1 in, I would get 1 still. If I put +1/2 right here, it wouldn't make a difference right there if that's positive or negative. You get the same value. So this appears to be approaching infinity. And 1 plus infinity would be infinity. So that 1 right there ends up being kind of unimportant. You can also think of shifting graphs, right? So this is 1 over x squared. What would this +1 do to that graph? It'll move it up 1. Is that going to change anything about your vertical asymptote? It will not. So this doesn't really affect your graph right here. If it was inside of parentheses, it would make a difference. All right, 7. I can do the limit of the top and bottom of this separately. So limit as x approaches -2 from the left of x squared plus 1 over the limit as x approaches -2 from the left of 1 over x plus 2. So for the top, you could just do direct substitution. -2 squared plus 1 is going to give you 4 plus 1, and you'll get 5. Okay. The bottom, if you try to do direct substitution, you're going to get 1 over 0, which tells you that limit does not exist. Okay, but it's either going to be approaching positive infinity or negative infinity. So that means, and it does matter which one it is, because if I have a positive infinity on the bottom, then I would be, actually, does it matter? Actually, it really doesn't matter. Here. Does it matter whether I have positive infinity or negative infinity right there? Let me think about that for a second. Because we're talking about what we're approaching, right? So if my bottom of this fraction is approaching positive infinity, I'm talking like I've got 5 over 10, 5 over 100, 5 over 1,000, 5 over a million. What value is my total expression approaching? 0. Okay. What about if it's negative? I got 5 over -10, 5 over -100, 5 over -1,000, 5 over -1 million. It's still 0. It's approaching from another side, but it's still 0, right? So actually, I don't even care on this one, whether it's approaching positive or negative infinity. It doesn't make a difference for this problem. So it's positive or negative infinity, doesn't matter. This is 0. Now, I will say it's like not mathematically correct to put those equal signs right there, because like the plugging in of the infinity and then saying it's 0, the idea is there. I don't care if you write it. I don't think you're going to see a free response question where this is going to matter, but if you were to, you probably shouldn't put those equal signs there. Okay, questions? Okay, so let me look at the book real quick and make sure this is what I want. 105. Let me see. Okay, this is fine. So 13 through 25 are just asking for vertical asymptote. So you should be able to look, 13 is 1 over x squared. You should be able to look at it and say x equals 0 is where your vertical asymptote is. So those should be fast. At first I was thinking it was too many, but those first ones should be able to be done in seconds. You're just looking at your denominator and telling where the vertical asymptote will be. A couple of them you might have to factor the numerator. I don't know if we do factor by grouping anymore. Probably not. Let me just tell you that 21 is none. Everything else should go pretty fast there. Some of them have weird stuff in the numerator, but does the numerator really matter? Not as long as it doesn't cancel with the denominator, it doesn't really matter. So those should be fast. Alright, I'm going to go a little easier on you and cut this off at 45. Just because I don't like these problems, and I know you guys won't either. So 37 through 45 odd, try to do those like I was doing those here. I want you to think about them and make a table by hand for whether or not it goes to positive or negative infinity. Once you get to 49 through 59, use your calculator. Okay, so graph it and look at it to tell whether it has a vertical asymptote. Try to use the 89 if you can. I know Desmos is easier. Try to get used to using that 89. If you're getting stuck and having trouble finding it, it's fine if you use Desmos. But we're working towards being able to rely on that 89 for that.